In this video, we're going to talk about a proof of the law of sines that is attributed to Ptolemy. So Ptolemy was, he lived a very long time ago in Egypt around the year 100 AD. So while we learned about the law of sines in class, it might surprise you to know just how old this idea is. So we need a couple of ideas that we didn't talk about in class that sort of come from geometry. So one thing is what we call a circumcircle. So a circumcircle is the circle that passes through all 3 points of a triangle. So in this picture you see here, you notice that each of these two triangles, all 3 of the corners of that triangle meet the circle. So this is called the circumcircle of those 2 triangles. And we're going to show that the value of the fraction in the law of sines is actually the diameter of this circle. So a couple of useful facts from geometry that we will need. This angle, ABD, is actually a right angle, and that has to do with the fact that the line A to D is the diameter. And then if 2 triangles have the same circumcircle and share one side, then the angles opposite the shared side are equal. So in the picture above, you notice that the angle delta and the angle gamma are both 58.99. And they could really be anything. Just the example that I happen to draw happened to have those measurements. Okay, so let's get started. So the first thing we want to notice is that angle ABD is 90 degrees. So we're first going to start with fact 1. And we're going to say that angle ABD is equal to 90 degrees. And that's by fact 1. So that just has to do with the fact that A to D is a diameter. So let me go ahead and actually label that on our picture. So each of these distances here, like from O to D, is going to be a radius as well as A to O. So each of these are going to be R. And notice that a diameter is actually just twice the radius. Okay, so back to what we were saying. Angle ABD is 90 degrees, so that tells us that triangle ABD is a right triangle. So triangle ABD is a right triangle. So this is important because with right triangles we can get all of our trig functions that we've talked about in class. So for any of the angles in that right triangle we could calculate the sine, the cosine, the tangent, and so on. But what we're interested in here is the sine because we're trying to get the law of sines. So we can calculate a sine for angle delta. Okay, so from class we learned that sine of delta is equal to the opposite side over the hypotenuse, which in the case of triangle ABD, if we look at the side opposite delta, that's going to be side C. And the length of the hypotenuse, well, the hypotenuse of the triangle ABD is that line A to D. So that line A to D, the length of it is equal to 2R. So we're going to write that in there. So now we've calculated the sine of delta. Okay, so now where do we go from here? Well, our goal is eventually to get this to relate to the sine of C. So let's just do a refresher and think about what the law of sines says. So the law of sines says that the sine of C, or in our case, we're going to call angle C gamma. So sine of gamma over C is equal to sine of beta over little b is equal to sine of alpha over A. So I've just named my angles with Greek letters here. So our goal is to get sine of gamma into this expression here. So this is where our second useful fact comes in. So our second useful fact says if the 2 triangles have the same circumcircle and share one side, then the angles opposite the shared side are equal. So if you look at the picture to the left, we notice that the triangle ABD and the triangle ABC share that side C. Okay, so let's make a note of that. So triangle ABD and triangle ABC have the same circumcircle and they share side C. So, by fact 2, we know that gamma equals delta. All right, so by fact 2, we can say that angle gamma is equal to angle delta. Okay, so let's see what we can get from this. Well, we've already calculated sine of delta, so if gamma and delta are equal, wouldn't it make sense that the sine of gamma should be the same as the sine of delta? I think so, so let's write that. So now we know that sine of gamma equals sine of delta equals C over 2R. So now what we can do is we can multiply 2R to the left and divide sine of gamma to the right. And what we get is that 2R is equal to C divided by sine of gamma. So that's awesome. We've actually gotten one of the fractions in the law of sines that we wrote over here. Okay, and furthermore, this fraction is equal to 2R, which is just the diameter. So let's see, we'll make a note of that here. So that's great. So now your question might be, well, how do we get the other two fractions? Well, actually, since we've done this one, the other two are done very similarly. We just have to draw some different triangles. So if we wanted to calculate the fraction for beta, we would have to draw a triangle CAD, where we sort of do the same thing we did here, except we have to draw it like this. So we draw a diameter this way, and then we would connect the triangle here. So this point would be on the circle there. And then if we wanted to find the fraction for alpha, we would do the same thing, but with a triangle BCD. So we would take that side A, and we would draw another side from B through O. That's crooked. Let's do that again. B to O, all the way to the other end of the circle so that it's a diameter. And then we would create the triangle with the point where it hits. So once we do this process 3 times, one for each triangle, we'll actually end up with the law of sines that we want. And so let's just write down our final result. So repeating this with 2 more triangles, we get the law of sines. Okay, so hopefully you found that kind of interesting. I know, I think it's always interesting to see when we find out, number one, how old some of this math we're learning actually is, and number two, it's sort of a different, more geometric way of looking at the law of sines. So hopefully you enjoyed this.